Hello, and welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be talking about the equations of motion. In the previous class, we developed them through a rigorous approach. Today we'll be talking more about their expansions and structure and the physical meaning of the different terms, which is so important to know and understand as an engineer before, of course, you might blindly apply the equations, which I never recommend. Remember, understand and keep track of the assumptions as we remain and find every particular equation. We'll then look at another set of equations which is alternative to the Navier-Stokes equations, which is of course by Boltzmann. And indeed, we can show that Boltzmann equations can be used through moments to find the Navier-Stokes equations. The Boltzmann equation can be important for rarefied flows. That is a flow where of course the continuum assumption might break down and we have very high speed velocities. We'll also talk about the fundamentals in physics of acoustics, which will play a central role in this class. We'll then talk briefly about the Bernoulli approach and equations and a review very briefly of thermodynamic laws. Let's get started. I personally like to start classes with a quote. Here's a particular sketch from one of many Leonardo da Vinci's notebooks. Indeed, he was thinking about aerodynamics. Think about how a very smart person like Leonardo da Vinci approached problems. He wrote in his notebook, "The object that strikes the air develops a force equal to that of the air that strikes the object. Observe how the beating of its wings, that is birds, against the air suffices to bear up the weight of the eagle in the highest and thinnest air. Observe too, conversely, the air fills the sails and pushes the heavily laden ship. From this, you can consider and understand that man, with great wings, acting against the resistance of air, might overcome it victoriously and rise above it." This is an inspirational quote and shows the kind of knowledge and in-depth thinking that Da Vinci was thinking about. This was written before the writing of Isaac Newton's Principia about his laws of motion. Yet he writes that an object that strikes air develops a force equal to that of the air that strikes the opposite, equal and opposite forces. Indeed, Da Vinci knew about these laws intuitively, but he did not write them down in the language of calculus. He also saw the coordination and ideas between the analogy of a bird flapping its wing and a sail of a ship. They're both aerodynamic problems which propel a vehicles. One is a flight vehicle of the bird, and the other is a sea vessel, which is the ship. He also understood that the density of the air, that is its thinness, changed with altitude. This was not really proven with excellent measurements until many years later. Therefore, he was much ahead of his time, and even his early vehicles, like you see in this figure on the right, had wings where a person lays down. Indeed, the earliest flight vehicles of the Wright brothers had their pilots laying down face forward, just like a bird. Indeed, Da Vinci and the Wright brothers were both inspired by the flights of birds. If birds have a fuselage, that is, their bodies are laying down and face forward, certainly people should be too in their flight vehicles. And that's why these designs had people laying down. Let's get started in this class. Remember, let's define fluids. A fluid is any substance that deforms continuously under a shear stress. Any matter that deforms continuously under any shear stress is a fluid, by definition. Here, in this class, fluids consist of liquids, gases, and plasmas. And we'll talk a little bit about plasmas, very little, but our class is mostly focused on gases, which have higher compressibility, as we discussed, the compressibility factor tau. Generally, liquids, just generally, not always, have much less compressibility, and so we won't consider liquids too much in this class. Now, the most simple definition of a compressible flow is that density varies as a function of time at particular spatial locations. This is a sufficient and necessary condition for, of course, the compressibility or incompressibility of a flow. But we showed in the previous class the most rigorous definition is that a fluid parcel maintains its volume as it is deformed in space. You can imagine that any infinite choices of fluid parcels in a fluid flow through space and time, which do not change their volume, would be considered an incompressible flow. We will not be interested in this assumption at any point through this class, except for a few examples done to counteract our fundamental ideas. In the previous class, we showed that the volume at time 1 equals the volume time 2, which would indicate that, of course, it's an incompressible flow for fluid parcels. That doesn't mean the control volume isn't changing volumes about the fluid parcel. Informally, you can just say that the density, of course, is changing in the fluid. Indeed, we discussed more rigorous definitions in the previous classes, but this definition will be sufficient for the rest of the class. I just want you to be aware it's not very rigorous. Now let's talk about supersonic versus subsonic flows. Supersonic flows, transonic flows, subsonic flows, we talked about these definitions. But remember, specific regions of the flow field might have the property that m is greater than u over c. Here, Mach number is defined as the local speed of the fluid divided by the local speed of sound. There's also a global Mach number. That might be the speed of the aircraft divided by the speed of sound at the altitude of the aircraft in the atmosphere of the undisturbed fluid. So mind these definitions. M equals u over c. U is the speed of the fluid and c is the speed of sound at one point. Therefore, m can change anywhere in the fluid. It can change spatially and temporally. If m equals 1, this is a so-called transonic condition. That is, m equals 1 equals u over c. Therefore, u equals c at m equals 1. Transonic condition, m equals 1. This is, of course, the singular point between subsonic and supersonic flow. Subsonic flow is where m is less than u over c, and supersonic flow is where m is greater than u over c. Typically, we do not discuss negative Mach numbers. Mach number is a scalar positive quantity. Therefore, transonic flows may exist anywhere where m is not equal to 1 also. In fact, transonic flow might be seen as a class of flows where you have supersonic and subsonic regions mixed in the flow field. Indeed, there's usually trivial solutions where m equals 1 everywhere in governing equations, the transonic condition. We'll find in the later part of this class how difficult transonics is, and it requires special mathematical attention. So we have flow regimes of creeping, subsonic, transonic, supersonic, hypersonic, and hypervelocity, and we've discussed these in the flow regimes part of the class. Now there's the idea of steady flow and unsteady flow. Of course, an unsteady flow temporally varies with time. It's dependent on time. It's temporally evolving. A steady flow may have unsteady motion in it. However, its statistics are not changing with time. The statistics of a turbulent flow, which is steady, is called stationary. So stationary statistics, that means statistics of the flow, even though it's an unsteady flow, are time invariant. We call a statistically stationary flow or steady flow. There's also steady laminar flows, where truly no variables in the flow are changing with time. In this class, we'll primarily focus on steady flows where the statistics and variables are not changing in time. So statistically stationary flows are steady turbulent flows, and we might view a steady flow as a laminar steady flow. In any case, we'll use this definition rather loosely and informally through the class. Remember, all turbulent flows, which are ones of engineering interest typically, are indeed unsteady, but they might be considered statistically invariant or statistically steady. We can show this graphically in class if you desire to look at it. Let's now look at the idea of viscosity. Viscosity, remember, is the shearing. That's the shearing force when you shear a fluid. It's the resistance of the fluid to shear. And of course, viscosity plays an important part in the stress tensor, which we defined not long ago. Let's look at this particular experiment in a figure shown here at the bottom of the page. The bottom plate, this is a plate drawn with hatched line, is stationary, and we move the top plate parallel to it at a velocity capital U. We can see at low speeds, the flow between the plates is laminar. If we move the plates fast relative to each other, instabilities will form, and of course a little turbulent flow will happen. Let's just let the plates move slowly by each other, and as long as the speed is slow, we'll develop a nice laminar linear velocity profile. Y is the direction and coordinate system at x0, y0 at one plate, and in the upper direction we have positive y. So the velocity between the lower plate and the upper plate is a function of y, and we might write its velocity component as u of y. It's only a function of y and not time or x or z. So the velocity profile is written by these vectors going to the right. Indeed, we have the no-slip condition at the lower stationary plate, where u of y is 0, and at the upper plate, u of y equals capital U. If we look at any particular fluid parcel or volume along this particular profile, we might write the fluid element like on the right. Indeed, there's some shear stress, which we write as tau, and tau indeed is equal to, for this simple system, as mu, the first coefficient of viscosity, which is a property of the fluid and dependent on temperature usually, times partial u partial y. Here u is only a function of y, so this means the derivative of u with respect to y, which is a constant in this particular flow. You can see the slope of u with respect to y is a constant. So here the shear stress is constant through the whole flow. And indeed, through measurement, we can approximate and try and estimate what mu is. In fact, today, through quantum mechanics, we can actually analytically derive viscosities for certain simple fluids. Nonetheless, let's look at some definitions of these particular fluids. Here in the upper right, we have an x-axis. This is the shear strain rate, partial u partial y, here, and the y-axis is tau. And so if we plot tau versus partial u partial y in this graph, we get a number of curves. If we find a linear relationship between tau and partial u partial y, we'll have straight lines. These are indeed what we call today as Newtonian fluids. If we have curved lines above or below the linear lines, they'll be called plastics or dilatants. These are also considered non-Newtonian fluids. And so plastic you might view as a type of fluid, which is, of course, continuously shearing with any type of shear force, which falls into our definition of fluid. In this class, we'll mostly focus on non-Newtonian fluids. And I often ask the class in person, what is the definition? Or can you think of examples of non-Newtonian fluids? My favorites are ketchup and honey. They both have non-linear shear stress, strain rate profiles. Let's talk about the difference between laminar flow, transitional flow, and turbulent flow. Laminar flow is like a laminate. Perhaps you've seen wood laminate, or you've looked in very, very, very slow speed fluids and you put in some dye perhaps, and you see that the flow moves like a laminate. You can kind of imagine that having maybe parallel parts of fluid in parallel volumes, and they just move across each other with ever crossing each other's streamlines. This would be an example of a laminar flow. It's smooth, non-chaotic, and there's no real fluctuations in it. That's laminar flow. And we might draw streamlines, parallel streamlines in a uniform flow without fluctuations, and that would indeed be a laminar flow. So you can have high-speed laminar flow, low-speed laminar flow. Now, sometimes the laminar flow profiles have inherent instabilities in them. Just like a dynamical system might be unstable and it'll go into a chaotic motion eventually, a fluid can be unstable. That is, the laminar profiles of velocities might contain instabilities, and a perturbation, like a small wave or vibration, will send the system into a chaotic state, which is turbulence. So that flow going under an instability in a laminar flow to turbulent, or is alternating between laminar and turbulent states, is called a transitional flow, because it's transitioning from a laminar to turbulent flow. In this particular case, you might observe this in your kitchen, for example. Perhaps you go to your faucet and you turn it on barely, and a little laminar rod, a clear stream of fluid comes down from the faucet. This is indeed a laminar flow. If we increase the amount of water coming out of the faucet, it might look clear, the rod of fluid coming from the faucet, in this case water, and it might look a little bit cloudy or jiggly or chaotic. That's because it's developing instabilities, and these instabilities are causing it to become turbulent. If we increase the water rate anymore, then the flow out of the faucet becomes chaotic, and therefore you can examine the flow regimes right in your kitchen sink by slowly turning on the faucet. A turbulent flow might be defined as one which is fully turbulent when the wave number energy spectrum contains non-zero energy at all wave numbers. Imagine I have a turbulent velocity field, and I take a Fourier transform in the x, y, and z directions. I can now plot, indeed, the Fourier transformed, that is wave number space instead of physical space, energies. If they are non-zero, I can then show that the flow is turbulent. This is a very mathematical definition. A more simple one, which is maybe physically understandable for now, is that turbulence is highly chaotic. And I think you know what it is. When you look at, say, cigarette smoke, the clouds in the sky, the water in the rivers, sometimes the airflow in our lungs, our breath, those are all turbulent flows. And aerospace engineering is no different. In fact, we should expect most aerospace flows to, of course, be turbulent in nature. And this is quite difficult to handle. Generally, in this class, we will be looking at flows which have very low to no turbulence. We'll have to treat the subject of turbulence in other classes, perhaps at the graduate level. We'll study these flows and assume that there's very little to no turbulence so that we can, of course, solve these equations. Generally, there's no analytical equations for turbulent flow. And therefore, we'll try and develop analytical equations and methods for flows which are not turbulent. There's another classification of so-called external versus internal flows. Here's some examples. An external flow might be one which is unbounded. An internal flow is one which is bounded by boundary conditions. That could be like solid walls. The upper left might be an example of a cylinder in a cross flow. It's an unbounded flow, and you can see indeed that there's a circular cylinder in a cross flow. A small turbulent wake forms behind it, and we draw streamlines around the cylinder. This particular streamline comes and it stagnates at the face of the cylinder. There's indeed a point of separation on the cylinder where there's turbulence in the background. It's external because, of course, it could be an external aerodynamics calculation like the lower left, where we have a simple airfoil, and the flow moves from left to right over the airfoil, and there's different flow phenomena forming around the airfoil. We'll study shock waves, a little bit about boundary layers, and the flow behind the shocks, all around this vehicle to approximate the drag. In the lower right, we have one particular example of a pipe flow. In this particular pipe flow, we have an internal flow and velocity field, and of course it's bounded on all sides, and so the fluid is like an interior. Interior flows might be like HVAC, flow through an aircraft engine, flow inside your veins of your blood, your lungs, pipes, some cavities might be viewed as internal flow. So you can probably think of many examples of internal and external flow. But at the end of the day, the equations of motion are exactly the same between internal flow and external flow. It's just that they have different boundary conditions. And this gives them unique properties in the final solution of the field variables. Let's review our differential form of the continuity equation. And here I've written the conservation of mass equation, which we developed in the previous class in 73. Let's read it together. Partial rho partial t plus partial xi of rho I is 0. So this means the change of density in the fluid at a particular point with respect to time is balanced by partial xi of rho I of 0. Think about this. This is almost like the divergence of rho ui is balanced by the time rate of change of mass in the fluid. We can also write 73 from Einstein notation into vector notation in 74. And so you can see partial xi of rho ui is nothing but nabla with the inner product of rho u in the second term of 74. We can then expand this out into typical Cartesian form or any coordinate system we desire. For example, 75 is the Cartesian form of 74. Partial rho partial t plus partial x of rho u plus partial y of rho v plus partial z of rho w is 0. So that's 73 written in Cartesian form as 75. What does this physically mean? The first term means the time rate of change of density at a point plus the derivative in the x direction of the density times the velocity in the x direction, plus the derivative of the density times the velocity in the y direction, plus the derivative in the z direction of the density times the velocity component in the z direction is all equal to 0. Now let's make the incompressible assumption. You can see that if density is constant, then it can come out of partial x, partial y, and partial z because it's no longer a function. It's just a constant value at that particular points. Therefore, we can bring it out, and we could write, indeed, that partial u partial x plus partial v partial y plus partial w partial z with a steady flow, partial rho partial t, is 0. is, of course, partial of a constant partial t is 0. And so for, a steady flow, we have the D'Alembert condition, or the inner product of nabla with rho vector u is 0. So this means the partial derivative of the velocity component in the x direction with respect to x, plus the derivative of the second component of the velocity vector with respect to y, plus the third component of the velocity vector with respect to z is 0. We can then further and state a steady assumption, which is compressible. The steady compressible assumption would be nabla.rho u is 0, or equation 74, crossing out the time derivative because it's steady, so rho can indeed be changing. That's a steady flow, will give us nabla.rho u is 0. So steady compressible flow and an incompressible unsteady flow indeed are two different things. Now let's return to the momentum equation. Here let's show the stress tensor on a particular fluid partial pictured on the left. The particular viscous stress tensor is written on the right, with components 1 to 3 for I and 1 to 3 for J. It's also symmetric, as we stated in the previous class. On the x face of the volume, we have 1, 1 component. In the x face in the y direction, a shear component would be 1, 2. And on the x face, which is 1, we would have a shear component in the z direction. That's 1, 3 in Cartesian coordinates. You can also see the second and third row are the normal stresses along the trace of the tensor. And the off-diagonal terms are the directions in the x, y, and z directions, respectively. So the second row is for the y face, and the third row is for the z face. It's simple to draw that and remember once you do it once. Now let's look at the momentum equation in its full form. Naturally, we relate the stress tensor through the first and second coefficient of viscosities in the equations of motion. Here we are in the full compressible differential form of momentum. That's written in 78 in Einstein or index notation. The rho times the material derivative, and it's a vector equation for I equals 1, 2, 3, for the first three directions respectively, is all equal to rho times partial ui partial t plus uj partial ui partial xj is equal to right-hand side stress terms plus body forces. Here, we define the stress tensor, which we called TIG in the last class, and here it's sigma ij, little, as equation 83. Once again, we have written as a negative of the internal stress, which is pressure, static pressure, times the Kronecker delta function, which is 1 for I equals j and 0 for I not equals j, plus the first coefficient of viscosity times these velocity terms, plus the second coefficient of viscosity zeta times the Kronecker delta function of partial uk partial xk. Notice, if we have incompressibility, then partial uk partial xk and partial uk partial xk in the first and second terms of the viscosity are indeed 0. Now look at the Cartesian form expanded. If we take 78 and expand it out for the x, y, and z direction, just like we did for continuity, of course, which is scalar, but now there's three equations which are in 3 dimensions, we can write it out in these full form. For example, the x momentum equation is equation 79, y is 80, and 81 is z. Let's look at the term itself. This second term, of course, is the material derivative, which is rho dui dt for I equals 1. The right-hand side is the expanded form of course, the stress tensor, partial sigma 1, 1, partial x, partial sigma 1, 2, partial y, partial sigma 1, 3, partial z, plus body forces. And this z should be an x here. That's a typo, excuse me. You can then see, of course, the second and third terms for I equals 2 and 3, summing over j equals 1 to 3 from 78. And so these are the actual equations of motion and compressible flow. We can also write 78 from index or Einstein notation into its vector form. The bold symbol denotes vector, u. You can try and write this out into Cartesian form yourself if you so desire. Let's now look at the differential form of energy. Here we have one written for specific energy, little e, which we derived in the previous class. We have rho of the material derivative V is equal to a heat transfer term and the body force terms, plus the viscous stress terms, which is doing work on the fluid. I've written down the definitions of these terms here, and I recommend you take a second to follow them. Once again, we made Fourier's approximation, Fourier's law, which works well for many different types of fluids, where K, of course, is a conduction coefficient. There are so many versions of the energy equation. We can write it in terms of enthalpy, pressure, temperature, total energy, specific energy. I've written two more in differential form in 85 and 86 for enthalpy, pressure, and temperature, respectively, for your convenience. Take a few minutes and study this particular slide, and pay special attention to, of course, the heat transfer term and the stress terms. We can also write differential forms for entropy, which is another law of thermodynamics. This is, of course, an inequality law from thermo, the second law of thermodynamics. Here, for calculately perfect gas and the perfect fluid, we'll say indeed that the flow is isentropic, and we'll get into these definitions later, and it could be reversible. Anytime you have viscous effects or heat conduction or heat coupling, the flow will be irreversible, and the entropy law will of course be written in terms of an inequality. And so it's not always useful for solving flow equations, but in this class we'll be able to use the entropy equation a couple times as an equality, making these particular assumptions that viscosity is zero. Let's review the full Navier-Stokes equations once again. We have continuity, momentum, energy written here. So here we have the compressible full Navier-Stokes equations with energy equation, but no gas law. These are the most important equations, of course, because they govern all fluid motion that we're looking at in this class and in most classes, except for rarefied flows. We've already talked about these equations in the previous class and this equation in class. So I think at this point, you can be expected to try and write these out in Cartesian form and understand each particular term and its meaning. Let's start using the following definition for shear stress. We'll say the shear stress is partial uj tau ij of partial xj. You can see, of course, this is a type of normalized force. It's a shear force for tau I not equal to j. We can also from now on, define a total energy. The total energy we'll call E naught. Naught is the sub-0 or sub-O written interchangeably. In 93, I say the total energy per unit mass is the specific internal energy plus the kinetic energy. That's ui over 2. Here, once again, we see two i's in a single term. That means we sum from 1 to 3. So that's u squared over 2 plus v squared over 2 plus w squared over 2, expanded out. We also define the shear stress term here formally. Tau ij is 2 mu of sij, and sij is a half of partial ui partial xj plus partial uj partial xi minus a third of partial ui partial uxi delta ij, where delta ij once again is the Kronecker delta function. We also define the heat flux terms with Prandtl number PR and lambda thermal conductivity. The ratios of specific heat, which we'll use throughout this class, is gamma. Gamma equals Cp over Cv, where Cp is the coefficient of specific heat at constant pressure, and Cv is the coefficient of specific heat at constant volume. This is completely familiar to all these equations down here from your thermodynamics classes, I hope. Here, P equals rho RT we will use if we deal with an ideal gas. E equals CVT, that's the specific internal energy, will go as C sub V times the static temperature T, and R is the difference, that is the gas constant of Cp minus Cv. So of course R, Cp, and Cv all have the same units. We should know, of course, because gamma is a non-dimensional number, which is the ratio of Cp over Cv. Typically air has a value of gamma 1.4. Remember these particular equations on this page by heart, because we'll be using them through the class, especially the ones on the bottom of the page in the last line. Let's take a second and a break to appreciate the mathematician Leopold Kronecker, who we named an important term of many equations that we developed so far in this class. He was German, and he lived from 1823 to 1891. And he was also a religious fellow, and he wrote, "God made the integers, and all else is the work of man." That's a pretty eloquent theory. Anyway, he worked on many different things. He was mostly working on number theory, algebra, and logic. He was born in Prussia, which is now Poland, and of course he did not have much interest as a child in running his family farming estate, and so he married an influential woman, and one person named Dirichlet introduced Kronecker to the Berlin elite society, where he started working in mathematics. And so I don't think his father was very happy about that. On the right, you can see his particular picture, and he's named today after many different theories, which I've listed in the lower right. Here we call him and refer to him as the Kronecker delta function with delta sub ij, which of course is 1 for I equals j and 0 for I not equal to j. Let's turn our attention completely now from the Navier-Stokes equations to acoustics. Of course, it is true that all acoustics phenomena that we typically study in aerospace engineering are completely contained in the Navier-Stokes equations, but we'll treat acoustics as its own independent subject. And in fact, we can try and derive acoustic equations independently from Navier-Stokes, but of course we can take Navier-Stokes equations and derive the acoustic equations more rigorously from, of course, the continuous deformation of a Euclidean space. Let's make some notes about acoustics now. Acoustic waves are extremely important in the aerospace engineering field, especially in compressible flow and fluid dynamics. As I mentioned, the equations of motion we developed completely contain all acoustic fluctuations as part of the solution of the full nonlinear system of equations. We might ask ourselves then, do acoustic waves exist in incompressible fluid? And this is something I want you to think about for yourself for a little bit. We might view and define an acoustic wave as a compression or expansion wave of a fluid. And so an acoustic wave, or waves in fluids, generally compress the flow or decompress it, which we call expansion. An expansion of a fluid is opposite of a compression. So fluids are compressed and expand. And through this class, you'll see a theme of wave science where we compress fluid and expand it through particular phenomena like shock waves and expansion waves, respectively. In fact, half this class is a study of shock waves. Now, waves in fluids can be very, 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 very large, like a shock wave, and raise the static pressure, which is the internal stress of a fluid, as we defined previously, by say 1 times 10 to the 5th pascals or even larger. 10 or 20 atmospheres is not a big deal. Or these pressures or compressions of density might be very, very tiny, like 1 times 10 to the negative 5th. Typically, acoustic waves have very mild, but do have compression. Now, what happens to the speed of sound in an incompressible fluid? Would it be 0, infinity, or a finite value? Let's turn our attention to the Boltzmann equation, and we'll return to acoustics in later classes to try to explain the formation of particular flow phenomena. Now, in Boltzmann theory, which is similar but different than Navier-Stokes theory, we might also define a distribution function f, just like we did way back in the beginning of Navier-Stokes. We might call that distribution function such that f of 2 volumetric integrals over x and v is an average number of particles contained in a volume element defined by the cube x of a fluid parcel. A velocity space element we'll call about v at time t. And so there's now a new idea of a velocity space element and an actual physical volume. We can then define the number of molecules in a gas as n at any x and t as an integral over f of the volumetric integral over v, the velocity space element. We can then once again define density as the particular mass times the number of particles as each particle has the same mass, which is simplified for now. Of course, this is not true in gases where molecules and have different masses like nitrogen and oxygen. And we can also define a velocity, which is 1 over the number of particles times the integral of f, which gives us an ensemble average velocity v. So here is the number density of the particles, and m is the mass of a single particle. Our velocity is an average plus a random quantity. So the average is u, and w is, of course, a random quantity. And this is the idea of the formation of Boltzmann equation, which is an alternative to Navier-Stokes theory, which you should be aware about in this class, but we are not be using the Boltzmann equation. Now, for flows with no collisions, we can indeed derive so-called Vlasov's equation. And this is an equation derived by Vlasov based on Boltzmann's theory, which might be viewed similar to the transport theory for any particular f. Here a is an acceleration, and f is a force acting on the particles. M, once again, is a mass. Now, particles might collide, and we might have a term that accounts for particles that end up in other volume elements. That is, if we distribute our volumes over a large space to model a fluid. The right-hand side term will give a net rate at which the particles are entering another element. And so we can take Vlasov's equation in 94 and add in a right-hand side to account for particles that are being transported from one volume element to another. And we might write a subscript collision to account for collisions. 95 is indeed the famous Boltzmann transport equation, which can be used to model fluids. Now, we might model through an integral collisions, and we'll just account for binary collisions between two particles for simplicity for now, which might write the right-hand side of 95, the Boltzmann transport equation, as the net rate at which particles are entering the so-called phase space element under consideration. We'll write that as R in R over R out. R in R out are the so-called rates at which particles are scattered in and out of a volume in the so-called phase space. We can then write R out as 97 as an example. What's important to see here in this equation is that an approximation of R out by taking the phase space and physical space integrals times a factor B, which is a factor that impacts the parameters. And Q is nothing but the differences of the velocities before and after the impact. There's also a collision term, which we can write in 98, dF1 dt of collision, which would be, of course, the right-hand side of 95. We can also write a similar equation for 97 with Rn. Here, these will represent families or ranges of velocities of the collisions. Now, if we take the Boltzmann equation with Vlasov and the right-hand side, and we take moments of it, we take the moments of the Boltzmann equation, then we can exactly recover the Navier-Stokes equations. I did not show us all the steps of it, but I just want you to be aware that you can use Boltzmann's theory to recover completely the Navier-Stokes equations theory and put his work on a physical basis instead of a purely mathematical basis like Navier-Stokes'. For example, we can take the moment of the top equation by taking integrals on the left and right-hand side, and then we can differentiate with respect to the particular variables of v and f and let f go to 0 and v go to infinity, and therefore q and f from the previous equations vanish, and we'll find this particular equation with respect to the number of particles. We then set q equals m, for instance, to recover the equation at the bottom of the page, which indeed, as you'll recognize, is the compressible conservation of mass equation from the Navier-Stokes equations. We can also let, of course, the middle equation with different values of q for, say, sort of mass, momentum, and energy, and exactly recover the momentum equations of Navier-Stokes. So some people today solve the Boltzmann form of equations because, of course, it models Navier-Stokes, but most people in practice use the Navier-Stokes equations. This is an aside in the class to show you that you do not necessarily have to use Navier-Stokes. It's just the most common and useful technique. You might ask yourself, who is Ludwig Boltzmann? Well, here's his picture on the right. He was indeed born from 1844 and passed away in 1906. He was an Austrian physicist and philosopher, and his greatest achievement was probably the development of the entire field of statistical mechanics, which explains and predicts how atoms, such as their properties like mass, charge, and structure, would determine the physical properties of matter, e.g. viscosity, thermoconductivity, and diffusion. So indeed, you can use statistical mechanics and quantum mechanics today to find and derive these types of properties which we showed and appear in the Navier-Stokes equations for different fluids. And so it's a completely closed and mathematical and physical subject. He also credited the idea of entropy, which is written on his grave. The exact definition of entropy, which you might not have learned in your thermal classes, is S equals K log W. Here, W is the number of states of the system, possible states of the system, K is the Boltzmann constant, and S, of course, is entropy. It's so famous that it's written on his grave. And here's a picture of a famous professor who's still living today and very active in outreach and mathematics in France, Cedric Villani, who's a field medalist. And he traveled to Boltzmann grave and posted his photo. I hope he doesn't mind me using it in my class, but I'm a great admirer. He's standing by Boltzmann's grave. There's Boltzmann himself. And on the top of his grave, up top, you see S equals K log W. Dr. Villani is a very interesting person, and I recommend checking out his blog for some interesting reading. Now let's take some time to look at particular examples of the flows and concepts we discussed in this class. Here's a particular flow over an airfoil. You'll see that they put in smoke lines over the airfoil. So the airfoil is in a wind tunnel, it's mounted here, and the airflow is coming from left to right. and these are basically streaks of smoke. You can see that these are relatively even unchained, and so we might unchanged relative to the y direction. We might say that this is a laminar flow above the airfoil and below. Now, once smoke comes along and it impinges on the front of the airfoil, and it might stagnate, and it ramps around the airfoil into what is probably a laminar boundary layer, and then it starts to change shape here. It becomes irregular. This is probably a region of transitional flow. And then behind the airfoil, something strange happens, and these little smoke becomes little relative puffs. In fact, there's something like a little vortex streak happening behind there, and it's transitioning to turbulence, which dissipates, of course, the smoke, disperses it through the volume. And so in this one picture, we see a lot of things happening. First, we don't know if the flow is incompressible or not, because we have no information about it. But we can see regions of flow which are considered to be stationary or statistically steady. We see regions of attached flow and undetached flow. We see a turbulent wake, and we see a transition. All things which we observed in this class and definitions. It's nice to see some pictures and examples to put our work on a theoretical and physical basis. Here's the famous faucet experiment I've shown you. This is in a chemistry lab with one particular nozzle, which is designed to have, of course, water hoses attached. The water's turned on here in the left, and a single rod of water comes down and falls down to the ground. You can see that this particular water stream is laminar. Why does it look and describe by the properties of laminar flow? Why is that? Think about that according to our definition. The middle picture, of course, is another flow regime. We turn the faucet a little bit more, and a higher speed flow comes out. Indeed, the Reynolds number is increased because the velocity is increased. And now you see slight ripples in the water, and of course, it's a little bit thicker because there's higher flow volume. And of course, you can see that there's some triangulations inside the beam of light, which is being bent by the water itself, of course, like a lens. This is a transitional regime, and it's transitioning from laminar flow to turbulent and vice versa back and forth. It's switching, like a mode switching in a dynamical system. The figure on the right, of course, is a turbulent flow. We increase the velocity of the flow, and the Reynolds number is higher beyond some critical value, and we see the stream and basically the turbulence within the water is diffracting all the light, and it doesn't go through the beam. You can try this in your kitchen next time you go to the faucet or a restroom, and I recommend you try it for fun. And you can kind of see and start to recognize in your everyday lives instances of laminar flow, transitional flow, and turbulent flow in nature and in physics. And we'll be dealing this throughout the class. Let's look at one particular example. Consider a flow with the following properties over a particular wing, which we showed 2 slides ago. The standard atmosphere will have values of P infinity, T infinity, and rho infinity. P we will call static pressure. T we will call static temperature, and rho we will call static density. The sub-infinity, sub means subscript, and infinity means ambient. That's like the pressure, temperature, and density of the atmosphere as if it was undisturbed by the airfoil. Now let's say the airfoil is traveling at 100 miles per hour. And we'll say that the airfoil velocity is u sub infinity, that's the ambient velocity of the airfoil relative to the fluid. Or we could say that the airfoil is stationary and the fluid is coming at it at 100 miles an hour, like we showed 2 figures ago. Now, somewhere above the airfoil, perhaps, we measure a maximum velocity of the fluid over the wing at 150 miles per hour. So this means the flow going over the top of the airfoil has accelerated from 100 miles an hour to 150 at some point. We would like to ask ourselves what percentage change between the free stream pressure, P infinity, and the max velocity point, U infinity, occurred. So there'll also be some P sub infinity associated with U at 150 miles per hour. So U, the max velocity, U with no subscript, 150 miles per hour. P, what is the pressure at that location of velocity at 150 miles per hour? Let's look at the solution, which I'll walk you through. Obviously, these air speeds are very low, and we'll assume that the flow is incompressible. Why? Because we can calculate the Mach number based on the temperature and speed of sound and ambient Mach velocity. Let's apply the so-called and famous Bernoulli equation. And remember, at this point from your previous class, you should have remembered the assumptions in the Bernoulli equation and how it was derived from the momentum equation alone. This equation is only valid for incompressible flow, so don't use it in this class after this example. The point of the example is to show air, even at low velocities. The famous equation can be written as P1 plus a half of rho U1 squared equals P2 plus a half of rho U2 squared. That's Bernoulli's incompressible equation. We'll derive the compressible form later in this class, so you don't have to make this kind of error again. We can rearrange the equation so we have a pressure difference. That's P2 minus P1 is a half of rho of U2 squared minus U1 squared. Here the subscript 2 and 1 represents states 1 and 2. State 1 we would replace with the ambient value sub infinity, and state 2 is the maximum value. Now at standard sea level we might look up rho infinity of 0.002377 slugs per foot cubed. And indeed, we'll note that 60 miles an hour is 88 feet per second, so we converted. This will yield, indeed, U1 equals 100 miles an hour, which is 147 feet per second. U2 is 220 feet per second. Therefore, the change in pressures from the ambient atmosphere at subinfinity or state 1 to the point of highest velocity might be a change of 31.8 pound per foot squared. Therefore, P infinity at 1 atm is 2116 pound per foot squared. Changing the pressure, P2 minus P1, that's the pressure difference divided by the ambient pressure at 1 atmosphere, is therefore the P2 minus P1, or P2 minus P infinity of 31.8 pound per foot squared divided by the atmospheric pressure of 2116 pound per foot squared. That ratio is non-dimensional. It's a change in pressure due to the velocity change, according to Bernoulli's equation with no losses in incompressible flow, divided by the ambient. Indeed, you'll get a value of 0.015. Putting it on a percentage basis by multiplying by 100, and we'll get 1.5% pressure change. The use of Bernoulli equation in high-speed flow will lead to significant error. What is the bottom line? A small change in pressure will change a change in density, which is even smaller. And so for maybe this low-speed analysis, we can get away with it because there's only a small percentage change. But for higher velocities, we'll have very large changes in pressure, which are not calculated correctly from the present equation. And therefore, we cannot use the incompressible approach. And we will look at these errors for incompressible versus compressible pitot tube measurements at high speed subsonic flows to show you how the air grows with increasing flow speed or Mach number. Remember, unlike incompressible flow, compressible flow will have kinetic energies which play a huge role in the compressibility and dynamics of the flow. The so-called thermal variables or thermodynamic variables will be interacting through terms in the Navier-Stokes equations with other field variables like densities and velocities, etc. All variables are strongly connected through the gas law and energy equation, which we cannot neglect in a compressible flow. Compressible flows require excellent gas laws and the units of the energy equation, which is the first law of thermodynamics. One might say and jokingly state that a perfect fluid, that is Eulerian, deserves a perfect law, and this is where the perfect gas law comes in. A perfect gas law is one in which the intermolecular forces are neglected, which of course is an assumption, but it works for a wide range of velocities at standard atmospheres. For example, we might write the static pressure, which is the internal stress of a fluid, times its particular volume is equal to the gas constant times the static temperature. V is specific volume. R is gas constant, which changes for each fluid. T is the static thermodynamic temperature, and P is the static thermodynamic pressure. Notice I'm saying static, 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 static. Later in the class, we'll introduce the idea of total or stagnation pressures, temperatures, densities, speeds of sound. So be careful. If we just write T, P, or rho without any particular subscript, you can assume that we're using a static value. Remember that. Now, we previously introduced the static pressure through the derivation of the fluid stress. Indeed, that is where the static pressure is defined and comes from. It can be physically interpreted as, of course, the time average force over a given unit area on a particular wall or within a particular surface within the fluid. Temperature is a thermodynamic quantity, but it's really statistical. Indeed, it's a measure of the kinetic energy within the gas, which is different than, say, the energy due to the bulk motion of the gas or fluid as it moves through space. For example, the kinetic energy is due to temperature, which is just measured with, of course, like in Kelvin or Rankine. This is different than, say, 1/2 U bar squared, remember, which is the idea of the kinetic energy of the motion of the fluid. There's other types of kinetic energies which we might discuss later in class. The most useful form of this particular law is P equals rho RT. Why is this? Because, of course, we have P, rho, and T formed and present directly in the equations of motion. The equations of motion don't typically have an explicit form for a specific volume, but really that's like an inverse of density with respect to mass. But we wouldn't want to have mass because that's a derived quantity anyway from the field variables. So P equals rho RT, of course, is the most important form which we'll use throughout the class. Remember that equation. Let's talk about particular gas constants like R, which appear in the gas law. Here, the universal gas constant is 8,314 joules per kilogram mole Kelvin. Remember that number. If the equation deals with particular masses, like air, we might write 287 joules per kilogram Kelvin. So when we use the ideal gas law, P equals rho RT, and our gas is air, we'll just simply use 287 joules per kilogram Kelvin in the equation. And don't worry about equation 100, which is, of course, the universal gas constant. Now, if we're dealing with particles and dealing with the Boltzmann set of equations, then we would use equation 102, and we finally define the Boltzmann constant, which is approximately, and we have much better precision today, 1.38 times 10 to the negative 23rd joules per Kelvin. We might ask ourselves, how accurate is the ideal gas law? And indeed, later in this class, when we look at hypersonic flows, we'll look and witness the breakdown of these horrible assumptions for highly compressible flows. Now, for low pressures and high temperatures, the ideal gas law will deviate about 1%. So for very low pressures and high temperatures, we might have to use real gas laws. For very high-speed flows, as I mentioned, we need a mixture or system of gas laws, real gas laws, or chemically reacting flow, or just dump them all together because we have a plasma. We also need to remind you from your basic thermodynamics classes the idea of internal energy and enthalpy. Here's where we'll remind you, and we won't look at this again in the class, but we'll use these variables and terms throughout the rest of the class. E is now internal energy per unit mass of the fluid. It'll consist of the kinetic, rotational, vibrational energies of the system of the molecules. And usually, we can write E as a function of temperature in the specific volume. H will be enthalpy per unit mass, and we'll certainly use enthalpy when we look at energy equations for certain problems. It's also a function mainly of temperature and pressure. If our flow does not have a chemical reaction in it, like we're not in a combustion chamber of an aircraft engine, we might say it's non-chemically reacting. It's not a reacting flow. And therefore, E and H are only functions of temperature, which is lovely. And that's how we'll work with this class mostly. So, internal energy per unit mass, enthalpy per unit mass, E and H respectively, only a function of temperature like 103 and 104. Indeed, if CV and CP are changing, then we would have to write E and H as integrals of Cp dt and Cv dt respectively. We can also write them in a differential form, and sometimes we can even write E equals Cvt and H equals Cpt when we make, of course, calically perfect gas assumption. This should be reviewed for you from thermodynamics. Let's now return to the ratio of specific heats. We define Cp and Cv as dH over dt at constant pressure and dE over dt as constant volume, which is Cp and Cv constants generally, if we make calically perfect gas assumption. Then we can write E equals Cvt and H equals Cpt with these assumptions. This is the so-called calically perfect system of equations for a perfect gas. As a general rule for air in aerospace engineering, or generally flows about Earth, you might assume that if the flow has a static temperature of less than a Kelvin, we'll say it's a perfect gas. If the flow has a static temperature of above 1,000 Kelvin to 2,500 Kelvin, then we'll have to say the flow is thermally perfect, and we'll relax these assumptions. If the flow in Earth is greater than 2,500 Kelvin, which can easily happen in re-entry vehicles, then of course there'll be chemical reactions and maybe even the conversion of the gas to a plasma, and then we'll have to deal with very difficult mathematics of electromagnetics and chemically reacting flows, and of course dissociated systems and ionization. Now, For thermally imperfect gases, we can make the following equations, which are algebraic. Cp will go as gamma r over gamma minus 1, where r is the gas constant and gamma is the ratio of Cp over Cv. And of course, Cv can be r over gamma minus 1. You should remember these equations too. Indeed, you can remember for air that gamma is 1.4 in this class. Technically, it's probably 1.39, but whatever. Here, gamma will vary for different kinds of gases like helium, air, nitrogen, and all kinds of different mixtures between 1 and 5/3. In fact, in the hypersonics model part of the class, we'll use gamma equals 1 to recover a Newtonian theory of aerodynamics, which is quite beautiful. But generally, we'll say gamma is 1.4 by default unless specified otherwise. In this class, we looked and reviewed the Navier-Stokes equations and their terms expanded out in Cartesian form. You should be able to expand these equations in Cartesian form and use them in both differential and integral form, from Reynolds transport theory to the differential equations. We also looked at the alternative formulation of the Navier-Stokes equations from Boltzmann equation. If you take the Boltzmann equation from the Vlasov equation and take moments and set Q equals, say, 1 m, or momentum, you can recover Navier-Stokes exactly from gas kinetic theory. Indeed, the purely mathematical way of deriving Navier-Stokes can be found from mechanics and statistics, and therefore we believe that the Navier-Stokes equations to this day are a wonderful and well-proven model of fluids. And that's why almost all the research we do today in aerospace, engineering, and other fields that does fluids is based on Navier-Stokes, unless the gas is a continuum, and then we might have to use Boltzmann equation, because of course the Knudsen number is too high, like we discussed in a previous class. We also discussed the most basics of acoustics, which we'll return to in the following classes. Then we looked at the incompressible Bernoulli equation. Never use this equation again in this class. In fact, if you always use the compressible form, you'll never have to worry about if you're using it correctly or not. We also basically reviewed the simple ideas of thermodynamics from chemically perfect gas, thermally perfect, the perfect gas law, CP/Cv, and of course the relation to gamma. Thank you very much for your time today. I'm Professor Steve Miller.